Okay, so anyone want to take credit for this? Thank you for the artwork. Anyone here do it? It's a mystery. Very nice. In case someone's too shy to take credit. Maybe it's a former student coming back. I don't know. Let's review where we were from last time. We were talking about ants on surfaces and the intrinsic geometry that they can perceive. Here, I'll take a picture. I'm gonna have to erase it. Seems like if someone does a nice bit of artwork there, right? Then today what we're actually going to do is we're going to prove the Gauss-Bonnet theorem. If we can get there, I think we can. And what do we do? Well, we were talking about using this orthonormal frame to do things like parallel vector fields and defining holonomy. If you parallel translate a vector around a curve, how much does it rotate? But there was really the important concept. What it came down to, like, what is it that we really needed? There was something we called omega 2,1 of v. Right, we put alpha prime, but it might as well be any vector, tangent vector v. And just to remind you, we have a coordinate chart that gives you an xu and an xv. And these are, we're going to assume they're perpendicular, as assuming f equals 0. Everything we're doing does not have to have f equal to 0. But, but just the formulas are more complicated if f doesn't equal 0. So what we're saying is choose a coordinate chart. There are many coordinate charts you can choose, right? So choose a coordinate chart such that xu and xv are perpendicular. And there's, I'm waving my hand saying that you can do that, right? But for example, latitude and longitude are coordinates where the lines of latitude and lines of longitude are perpendicular, right? And so we're just saying do that more generally. It just makes the calculations easier. And then given that means that xu and xv are perpendicular, but they have different lengths. Xu has length square root of e, right, by definition of e, and xv has length, xv dot xv, which is g, so the length is the square root of g. And so if we divide by those quantities, then we get an e1 and e2, which are orthonormal, and then they're also perpendicular to u. So in total, we get this e1, e2, u orthonormal frame, where e1, e2 spans the tangent plane at each point. But then we want to know how much is that e1, e2 rotating at each point, and that's what this omega 2,1 was. You may recall from last time, is that you take the covariant derivative of in the direction of v of e1, and then you take that and then dot product it with e2. Right. That was our definition of omega 2,1. And this has all the information in it of how much that frame is rotating. You may recall that when you say, hey, how much, what is this vector? Well, the point is the rate of change of E1 is just in the E2 direction. Well, how much into E2 direction? That much, right? And then however much E1 is rotating is however much E2 is directioning in the negative E1 direction, right? And so that's what we found out last time. So this is like the new interesting quantity, just telling us how much that frame is rotating. And there's something very interesting. This is essentially what we're going to learn today, is that and this is omega 2,1 is called a one form. Anyone here ever hear of differential forms before? Different classes, right? So I don't want to get into it too much. One forms are things that you can integrate over a curve. So remember the line integrals? You're integrating one forms. Okay. And you can take d of a one form, and that's what's called is Green's theorem. So just to give you some context, so we're going to use Green's theorem today. So let's go ahead and write it down. Green's theorem. Green's theorem, as we will use it, just to use the annotation of the book here, is that if you have, we'll do it around a curve here, bounding a ball B. I'm copying the notation of my notes because it's probably the same notation in the book. But if you take the integral around the boundary of that region, and we're in the two-dimensional plane here, but we're in the UV plane. Okay, so just whoops, U and V. So if you have a region in the UV plane, and you look at the integral of P times du plus Q times dV. So in your integral multivariable calculus class, you may have seen this as dx's as dy's instead of du's and dv's, but just renaming the variables. Then this is equal to the integral around the two-dimensional region. So that's what Green's theorem is. It turns a line integral around a one-dimensional thing to a sort of a double integral over a two-dimensional thing, right? The solid B on the inside. And so then when you say, okay, well, what is the thing that you integrate here? Well, it's something du dv, right? Because that's the thing you integrate to get area. And what it ends up being is the partial derivative of q with respect to u minus the partial derivative of p with respect to v. So that's Green's theorem. And by the way, this right here is a one form, in case you're, just to get the notation down. And this right here is an example of a two form. Okay. One forms are things you integrate over one-dimensional things. Two forms are things you integrate over two-dimensional things. And in general, n forms are things you integrate over n-dimensional things. Yes?
The equation over there, the dot product is supposed to be on the other side?
Oh, it doesn't matter. Dot product is symmetric. The dot product of two vectors doesn't matter on the order. The cross product matters.
I mean the other side of the equation.
Which equation are we looking at? This
The one you're pointing at, yes.
To repeat, I don't even know what you're asking me to do.
I thought the equation is supposed to be the upside down triangle thing.
Yep.
I don't speak math.
The covariant derivative, yep.
Equals omega times 3 upside down thing.
This is E.
Okay, E.
E.
Good.
Okay, you were saying that's a 2 and that's a 1?
I'm saying
No.
the 2 should be on the other side.
Put this over here?
Yes.
So E2 dot product this?
Other side of the equation. So
Oh, E2 dot this?
Yes.
Okay, okay, so let me just summarize this a little more, okay? I think I understand what your question is. Okay, so this is the new thing, okay? So what I have here I'm pretty sure is correct, but I'm never 100% positive because I'm 53, and frankly I'm losing it a little bit. Okay, so it's just not, I make mistakes a little more than I used to, just a little bit. But I think what you're referring to is, where this came from was that if you take the covariant derivative of E1, right? Then this was omega 1 times E1 plus omega 2 times E2, okay? And for that, and then the same thing here is when we take the covariant derivative of E2, the point is this is the linear combination of E1 and E2 as well. And then what we did was we filled in with these coefficients omega 1, 2 here and omega 2, 2 there, right? So this is where the definitions of the omegas were. And then we argued that, look, the rate of change of E1 is always perpendicular to E1. That was our trick we use all the time. So this term here goes away. Right, when you have a unit vector, it can only turn to the left or to the right. You can't turn in its own direction, right? And so same thing for E2. This term isn't there. And then we were also able to argue that, in fact, omega 1, 2 is the negative omega 2, 1. And that this was the tricks we did. So this was negative omega 2, 1 because of some of those two terms add up to 0. And so I think it's this equation as you're referring to. Yeah, so it is, but that is also true.
So it's
So that, I can go ahead and put this over here now, omega 2, 1 times E2, right? So if you're like, okay, look, I know that E1 is changing in the E2 direction. I know that by some amount. and E2 is changing in the negative E1 direction by some amount. It turns out they have to be the same amount, right? Because however much E1 is rotating is how much E2 is rotating as well, right? And so if you look at this picture, if E1 is rotating towards E2, in other words, we're twisting this way, right? That means E2 is going that way, which means it's rotating in the negative E1 direction. And so this right here makes intuitive sense as well as mathematical sense. Does that make sense?
So it's vector equals scalar times.
So this is vector equals scalar times vector.
And that's not a dot product.
And this is,
Okay.
right, that's just the regular product. And this is, scalar equal vector dot product vector. So yeah, my dot products are, I think I actually did that pretty well, but let me make it extra thick, right? That's a dot product and everything else is a regular product.
Amazing. Thank you.
Okay, great. I'm glad you asked that. Just, let's summarize. Because actually, these formulas are almost the same, except that's over there. It's like, oh, wait a second, did I miswrite something? But no, it's an interesting coincidence that the formulas are very similar, aren't they? Okay, so this explicitly shows you that this omega 2,1 is how much the frame is rotating, what we might call counterclockwise. And then this is the formula for it, how much it's rotating. Okay, any other questions or comments? Now, what I just wanted to say is this omega 2,1 is also a one form. Now you might say, what? Does it look like a one form? I mean, that looks like a one form, right? That's a line integral. I can integrate that over a one-dimensional thing, right? But let me tell you that the one forms are really to be thought of as two different ways. There are things that you can integrate, but there are also things that give you a number when you put an orthonormal basis of vectors into them, or actually any in vectors. So this du dv, if you really get down, what is integration, right? What integration is, I split my let's take the two-dimensional region here up into a bunch of tiny little parallelograms, right? And those parallelograms, they're nearly parallelograms, right? Those parallelograms have two vectors that define the parallelogram. And then somehow or another, you're going to plug in those two vectors into this du dv. And in this case, it's going to tell you what the area of that parallelogram is. Okay, so you plug in two vectors, it gives you a number out for a two form. For a one form, you plug in one vector and it gives you a number out. Well, this plugs in one vector and it gives you a number out, so technically that's a one form, actually. It's something you can integrate this, and we are going to integrate this today along a curve. And we're going to see what you get. And it turns out, and then we're going to apply Green's theorem, and it turns out that the integral, so let me tell you the more general formula. You guys know Green's theorem here, but there's something called the generalized Stokes theorem. Let me put this down here for comparison. Raise your hand if you know the generalized Stokes theorem. Nobody? It's unfortunately, generalized Stokes theorem? But not Stokes theorem, the generalized Stokes theorem. By the way, you think you might know? Okay. Let me say that I think a generalized Stokes theorem is arguably the center of mathematics. Like if I had to pick one theorem and say that, yep, that's the smack dab center of mathematics, it might be the generalized Stokes theorem. Okay, because it has so many applications. This is the fundamental theorem of calculus generalized to as much as possible, basically. And the fundamental theorem of calculus is just, integral of f prime of x dx equals f of b minus f of a. There's part 2 as well, but Okay, so generalized Stokes theorem is the statement that the integral over the boundary of some region of some differential form is equal to the integral over that region of d of that differential form. And so I just want to point out how beautiful that statement is, right? You have here you have a two-dimensional region B, and its boundary is a one-dimensional curve. More generally, you can have a 17-dimensional region R. And do y'all mind if I don't do 17 integral signs? Okay, so we don't do that, in graduate level math. We do one integral sign no matter what the dimension, because otherwise it gets kind of ridiculous. Okay. And so we're integrating over, say, a 17-dimensional region R. Its boundary is 16-dimensional. And there's an identity between the integral over the region and the integral over the boundary of the region. And you're integrating something over the boundary, and you're wondering, well, what's d omega defined to be? I'm going to give you a really nice definition. You ready? D omega is the thing that makes this theorem true. Okay? It's just the thing that makes this theorem true, that's all. Because now, it gets a bit more technical if you want to know, okay, well, what makes this theorem true? Oh, okay, well, you know, might have to spend a couple of weeks on really getting differential forms down, dotting the i's and crossing the t's. There's a lot to it. It's a whole subject, right? You know, you can spend 2 or 3 weeks on it in a class to really get a lot of the details. But here, I just want to point out that this is omega, and that's d omega. Okay, this is a 1 form. In this case, this is a 1 form. We could call it omega. And this is a 2 form d omega. Right? It's the thing that makes it true. And if you say, well, how do you prove Green's theorem? Let me just point out that at the heart of it is the fundamental theorem of calculus. This is line in, the single variable calculus, fundamental theorem of calculus, which you learn in calc. What is it? 111, 112, 112, I guess, with integrals. Okay.
What's the sort of like
Math 112.
so on the left hand side? What are you integrating with respect to?
Here.
Yeah, at the bottom.
You're integrating a differential form over something, so it's something that looks like
Okay.
this.
Oh, okay.
Yeah. So yeah,
Okay.
it's so omega. It would be this whole thing here with the du's and the dv's.
Mm.
So anyway, that's the whole subject. We don't have time to do that. The whole subject today. I just want to point out that there's something really nice, and that is, you ready for this? The integral. Okay, let me put it over. The integral over the boundary of that region B of omega 2,1. Now this is not just any omega. This is omega 2,1, right? Omega 2,1. This is a 1 form because why? When you put vectors in, you get numbers out. This is equal to the integral over B of d omega 2,1. But here's what's kind of interesting about that. The integral over, which is going to be something like of this form, but it turns out d omega 2,1. But then here's the kicker. D omega 2,1 is equal to the Gauss curvature times the area form. Okay, so that's the identity that's like, oh my God, right? The d, when you take the differential, when you take d of this omega 2,1, is the Gauss curvature times the area form. Okay, I'm going to show you that explicitly now. Okay, and again, what is this d defined to be for our purposes? It's just the thing that makes this theorem true. In other words, it's Green's theorem. It's this. If your 1 form is that, then d of it is that. Okay, by definition. Okay. So how do we do this? Well, we've got some more stuff to do. Anyone here come in and want to take credit for this artwork? Anyway, thank you for it. Yes.
I feel omega 2,1 is a scalar and 1 form's taken a vector. Is there?
Omega 2,1 is a functional. It's a number once you plug in a vector v, but it's a function of some vector v. It's a real value function. So it's a scalar once you plug in a vector.
Oh, so omega 2,1 is the 1 form.
It's the 1
Oh,
form.
okay.
Yeah. And then when we take d of it, so if that's a 1 form, then this is the 2 form, right? So I'll show you all explicitly. But so the nice way of saying what we're about to show is that d of this omega 2,1. I mean, this omega 2,1 is a 1 form. And now you know what a 1 form is. Whenever you see something that eats a single vector, you're like, oh, that's a 1 form. And then the natural question is, oh, okay, well, if that's a 1 form, then what's d of it? I mean, and then kind of apply Stokes' theorem and see what I get, right? Or in this case, it's just Green's theorem. So, by the way, the generalized Stokes' theorem, yeah, learn that. But you don't need it for this class. We're just doing Green's theorem. It's not a two-dimensional thing. So, if you never want to go over 2 dimensions, then there's no reason to learn a generalized Stokes' theorem. But let me tell you why it's kind of nice. Is that remember there's this thing called the divergence theorem? Remember this thing is called the Stokes' theorem? And then you have Green's theorem. Turns out they're all special cases of the generalized Stokes' theorem. It just unifies all that. All of that's the generalized Stokes' theorem. That's why it's just cool that all. I mean, this looks so much simpler than, let's say, the usual Stokes' theorem. Right? You know, the usual Stokes' theorem, they got curl and all that other stuff, right? It's like, whoa, what's going on, right? Line integrals, and it's like kind of confusing and always bothered me a little bit. And it's like, gosh, why is that true, right? The divergence theorem always made more sense to me. But then when you realize just special cases of the same theorem in, then, you know, that's it's nice. And plus that works in higher dimensions. You know, if you know, what is curl in 17 dimensions? Like, oh, I guess a little confusing, right? But that doesn't, right? That's just a formula, and you figure out what it is, and there you go.
What are the sort of like limitations on omega? Like, does it have to be, I assume it has to be differentiable? Does it have to be like second differentiable?
Yeah. I mean, it needs to be, let's say, for example, if it's C1, that would be certainly adequate.
Right.
And our regions are, you know, reasonably nice. I'll refer you to the literature on the weakest regularity. I tend to like to think of things as smooth and the limits of smooth things, and the question is, like, what kind of limits can you take? Okay. So let's see here, where are we? Okay, so now we've got a bunch of a calculation to do. You remember last time that we had this definition for omega 2,1, but we also figured out that omega 2,1 of alpha prime, let's see, do I have room here? Yeah, I think so. And remember, this is a unit speed curve, right? When we plug this in, that this equaled the geodesic curvature minus d theta dt. Okay. I think we wrote it the other way last time. It was like the geodesic curvature is this plus that, right? Okay. But let's write it this way this time. Just put the d theta dt to the other side. And actually, t equals s. Okay. So I think the book has this as s actually. But I think it had as t. I'm 100% positive what they did in the book. Let's make everything in terms of s. So if you see a t, it's also just s, because everything is parameterized by arc length. And so we proved that last time. We'll do s for everything. Okay. And just to remind you why this actually makes total sense, right? Is that, you know, put the d theta ds to that side, right? And by the way, what's the picture here? This is where we have alpha prime of s equaling cosine theta E1 plus sine theta E2, right? So what theta is, it's the angle that you're you know, so you have a curve here, right? That's probably going to make a loop. This curve is your alpha prime of s. Is your alpha of s, parameterized by arc length. And what this is saying is that the geodesic curvature, which tells you how fast your curve is curving, is equal to how fast the frame is curving plus how much the curve is curving with respect to the frame. Make sense? Or everything's measured in terms of d theta, you know, angle, radians per arc length. Right? And so now let's take this curve here, and let's also think of this curve back over here. And let's suppose this curve here is parameterized by u of s comma v of s. And of course this is the mapping x of u comma v equaling and going into this three-dimensional space over here. And so and now I want to follow the book. I apologize. I called this curve alpha of s, but I think in the book it's beta of s. So this is beta of s, and then this is beta prime of s. Okay. And so the key point is that beta of s, which is the curve over here, is equal to x of u comma v, but where the u are going along this curve here, u of s comma v of s. Okay, so we have this curve in the UV plane. When you compose it with x, it gives you the curve in your surface. Okay, and then what so I want to integrate this one form, omega 2,1, along this curve. I'm showing you how to do it. Okay, what I'm doing is, you may recall from your multivariable calculus that first you parameterize the thing you're going to integrate. Right? It was always the first step, right? And so this is our parameterization. And then let's do a computation. Beta prime of S is equal to, well, chain rule, right? So you got the partial derivative in the first slot times U prime of S, right? Plus the partial derivative in the second slot times V prime of S. That's just the chain rule. Fair enough? Now, what is the integral along this curve here? Let's go ahead and make this curve close up. All right, so it starts and ends at the same place. And we have a region here, and we're calling that region B. I guess that's what the book does. B for ball, right? It's topologically a ball. And then we got the boundary of B here, right? And so what we want to do is we want to integrate over the boundary of B, right, which is the curve beta of omega 2, 1. Okay? Which is a 1 form. Okay? That's our left-hand side here. Okay, we're the left-hand side of this. Okay, so what this means is you parameterize this thing here. You're parameterizing with beta. And so then what it means is we're going to integrate along the curve A to B, S equals A to S equals B, of omega 2, 1 of beta prime of S ds. Okay, so that's the definition of how you integrate. A 1 form is you parameterize your curve here, and then you plug in the velocity vector of your curve as the vector to the 1 form, and then multiply by ds. And that's why anything that eats vectors and gives you numbers out is something you can integrate. And so then you say, okay, well, but what is this? We need to figure out what is that. Okay, well, we have a formula for it right here, right? And we have a formula for it right here. And so let's kind of plug in here, integral from A to B. You know, just to remember what are A and B. The point is this, it's the beginning and the ending point, right? You go around and you start and end when you, it's S equals A is the beginning and S equals B is at the end. And so it's the covariant derivative in the beta prime direction. Beta prime of S is right there, of E1 dot product E2. Okay? That's the definition right here. Okay, now what is it? Well, this E1 is defined to be xu over the square root of E. Okay? I'm skipping a step. Let me not do it, okay? My notes could be a little better, so that's why I'm going a little slower here. The point is, this is going to be, I'm going in the direction of beta prime of S. So this means I'm going to get U prime of S. And then I take the covariant derivative of E1 and the direction of xu. And then plus V prime of S times the covariant derivative of E1 in the direction of xv. Okay? And you take all that and you dot product it with E2. Okay? So all I did was use the fact that beta prime of s is a linear combination of xu and xv with these coefficients, okay? Using the linearity of the covariant derivative. And then you stare at this for long enough, and you realize that this is u prime of s times, well, wait a second, what is E1? E1 is just xu over the square root of e. And then we're taking the covariant derivative in the xu direction, but that's equivalent to taking a u partial derivative. Okay. And then, again, we have E1 here, and it's times v prime of s. And then that's xu over the square root of e. And now we're going to take the covariant derivative in the xv direction, but that's where you hold u fixed and increase v, right? So that's equivalent to a v partial derivative when you express it as a function of u and v as opposed to a function of x, y, and z. So that's everything inside the parentheses here. And then you dot product it with E2 times ds. Script E2. And then we do some calculus. Quotient rule, right? Always my least favorite rule.
Yeah.
But, it's all right. So what do I have? I got u prime of s times, we got an e on the bottom, right? You take this thing and square it, right? And then you got to take the derivative of the top thing, so that's going to be xuu, so that's a vector, right? Times the square root of e, I think. Yep. And then you got to take, and then minus xu times the derivative of the square root of e, which is 1/2 e to the minus 1/2, right? Times eu. So that's the first term there. Okay, just doing the quotient rule. Whoops. That is this term here. It's already times u prime of s. And then plus v prime of s. And actually, okay, that's fine. Let's do it like this. V prime of s times, okay, we got to take the derivative of this quotient rule. You square the denominator there, right? And then you do xu, you take its v derivative, and so you get xuv, and then times the square root of e, and then minus xu, times the derivative of the square root of e, which is going to be, again, 1/2 e to the minus 1/2 ev, I think, right? And then you take the whole thing, dot product it with E2 ds. Okay. And then there are some tricks that we've done before. And I'm not going to, let me, I'm a little short on board space, so let me just remind you that one of the easy tricks was that if you take GU over 2, remember what G is? That's, in other words, this is going to be, G was, let's see, E, F, G. G was xv dot xv, right? So you take xv dot xv, then you take the u derivative of that and divide through by 2, right? And remember what you get when you do the product rule here, you get an xv dot product x, or let me do the second derivative first, xuv dot product xv, okay? And then remember, that was the easy trick. The harder trick was that negative EV over 2 equals, and there was actually 2 steps to the trick, okay? Because it uses f equals 0, and you get this equals xuu dot xv, okay? And I'm just copying that from the notes. You just looked that up later, okay? We did the trick before, okay? But it's using a trick like this, but twice, so 2 steps, okay? And so we can substitute that in, because notice what we have here with E2. What is E2? E2 is xv over the square root of g. So in fact, let's just put xv over the square root of g here. So what we're going to get is an xv dot xu, which is 0, by the way, right? Because we're assuming f is 0. xu dot xv is 0. And xu dot xv is 0. Okay? So these terms are going to cancel. But then we have an xuu dot xv. That's right there. That's going to be a negative ev over 2. Okay? And then we have xuv dot xv. That's right there. That's gu over 2. Okay? And so when we do that substitution, then what we get is the integral from a to b. Let me simplify this of negative EV divided by 2 square root of EG plus GU divided by 2 square root of EG. Oops, sorry. All right, I'm not liking this. I feel like it's too cramped here. I'm going to put it somewhere else. I'll go ahead and put it. Integral a to b of negative EV divided by 2 square root of EG times du ds plus gu over 2 square root of EG times dv ds ds. Okay? So that's just algebra. Notice that where I had a u prime of s, I replace that with du over ds. Where I have a v prime of s, I replace it with a dv over ds. There's a reason. I'll tell you why in a second. Same thing, right? Just notation. Those terms canceled. And then you got your square root of g here. There you can see it's not showing up, right? And everything else is just algebra with these substitutions. Okay? And it's all in the book, by the way. Okay, so you can check the algebra as carefully as you like. Okay. Now, why is it kind of nice to write it this way? Because notice how these ds's cancel. This is actually a line integral. Okay, in other words, if I don't have to, if I don't want to, but I could literally erase this ds, erase that ds. I could just put a du there, something times du plus something times dv. That's just like a line integral that you have from Green's theorem here. In fact, let's just go ahead and do that, I guess. Might as well. I don't need to put the parentheses in here anymore. Yeah. Okay. It's just a line integral. Yeah, and well, we've got a formula for line integrals. It's called Green's theorem. I have something in the form p integral of p du plus q dv. I know what to do with that. I can turn this into this is an integral from a to b in the corner chart. Notice that we're in the corner chart here. Okay. Yes.
In the box, the e partial with respect to b, should that not be x in the box in the middle? That, yeah, should that not be x uv dotted with x u?
Well, I skipped. There's 2 steps in the dot, so it's not something I can check in my head. But let me just check my notes. Negative ev over 2 equals xuu dot xv. That's what I have in my notes. But I can't. Okay. Shall we? Did you look it up in the book? Am I wrong?
No, I was just thinking, is it not kind of symmetric to the equation?
Oh, there's 2 steps missing here. Okay, let's do it. Let's do it real quick, okay? Okay, I'm gonna do it right here, then I'm gonna erase it. Okay, is that fair enough? This is our second time to do it, but I totally get it. You look at xuu dot xv, and you're trying to figure out how do I express that in terms of my EFs and Gs, right? And then you're like, oh, okay, well, if I take xu dot xv, right, that's f, right? I happen to know that's 0, right? But and let's take a u derivative of that, right? Then that would give me the term I want. But then it also would have an extra term, so I'm going to have to subtract off the xu dot xuv. Right? Now that's f, and that's 0, right? So I can say this is equal to negative xu dot xuv, right? And then I have to keep on going, and I have to say, but wait a second. Oh, okay, I see what this is. This is negative 1/2 xu dot xu, then take the v partial derivative. Okay, and then xu dot xu, that is e, so I get negative ev over 2. Okay. Expect that to be on the final exam.
Okay.
It's a good problem, right? I've done it before. It's no big secret. It's on the previous exams too, probably somewhere, right? So, I mean, look, it's 50-50. I have a problem. There's only a certain number of problems I can ask. So it's like I have a pool of like 15 problems I like. I'll choose half of them to be on the final exam or something. I don't know. It'd be one part of one problem. So. Okay, so anyway, that's this identity here. So now we've proved that. Okay, and we did it earlier in the book when we were doing computations with. Remember we computed the Gauss curvature? We had to do these same tricks. Any questions before I erase this? Okay. All right, and so now we apply. Now here's what I want to emphasize something. We started out by integrating on the surface here, right? But then how do you integrate something on a surface? Well, you choose a coordinate chart, you parameterize it, and then next thing you know, you're integrating from A to B. S is going from A to B, and so really it's just a single variable calculus integral, right? And then it ends up being a parameterization of this integral over here in the coordinate chart, right? So when we right here it's single variable calculus. It's some expression times ds. That's single variable calculus. But when you do this right here, now it's a line integral in R2. So now we're doing multivariable calculus. We're not even doing differential geometry. We're doing math 219 or 222 or 212, depending on the case. So we're doing an integral in the xy plane, actually the uv plane, right? Okay. And so now we just apply Green's theorem. And so this is equal to, instead of the integral around this boundary here, which, we're calling this B, and we're calling this the boundary of B. Do you all mind if we just go ahead and use notation and go ahead and call this B and the boundary of B also? Technically, it's not the same thing, right? Maybe I should call that B tilde or something, right? Okay, fine. I'll do it if you insist. B tilde. But mathematicians, we often abuse things like that. We're like, but it also can be a point of confusion, right? So actually, one thing I could do is instead of integrating from A to B, I could say this is the integral over the boundary of B tilde, right, in the coordinate chart, over there. I guess more technically that's correct, actually. Right? Because there, if we take A to B, it says S goes from A to B, but there is no S in the integral now, right? So you're actually integrating over that curve. So we apply Green's theorem, right? And so then we get the double integral over B of notice that you get the thing that has a dv, you take the u derivative of that. So we're going to take the yeah, okay. So we're going to take the u derivative of this and the negative v derivative of that. Okay, so whoops. So then what we get is we can factor out a half in both cases. And we have GU over square root of EG, take the U partial derivative, and then minus the V partial derivative of this thing. Let's factor out the half again. The minus times minus becomes a plus, and we get EV over square root of EG, and then take V partial derivative, du dV. Now, if you stare at that for a while, you're like, gosh, that seems familiar. Seems familiar. It's not quite something we've seen before, but it's similar to something we've seen before. And so we're starting to say, wait a second, what's going on here? And then what we do is we look up the formula for the Gauss curvature that we computed. And we realize it's exactly that except for a factor. Right? We are like this close to the Gauss curvature. Right? And let's go ahead and factor out a minus sign, because there's a minus sign in the formula for Gauss curvature. In fact, the formula for Gauss curvature was minus 1 over 2. And then what you had to do is you have to put in a square root of EG there, okay? But otherwise, it's what you have here. And so let me just copy this in first. All right, and then you have a du dv. Leave a space if you're taking notes, because I want to put something here. All right. So I haven't changed anything so far. All I did was introduce two minus signs that cancel. Okay. Haven't changed anything so far, but I can make this Gauss curvature if I put a square root of EG here, and then that is Gauss curvature. So then I need to put a square root of EG here. Okay, just to factor that out. And then I'm like, wait a second, that's the Gauss curvature. And so what I have here is an integral, the negative integral over the Gauss curvature, times whatever this is, and then you stare at that for a second, and you're like, wait a second, that's just the area form. Okay, now you might say, wait a second, I thought du dv is what you integrate to get area. Well, yeah, du dv is what you integrate to get coordinate chart area, right? But if you want to get area over here in the actual real world, on your actual surface, right? Remember that that xu is stretched by that xu here has length square root of e, and xv has length square root of g. So this makes a rectangle of area square root of e square root of g. Fair enough? And so you got to stretch by this factor to actually get the area form on your actual surface. And so what you actually have then is an integral over b tilde of the pullback of these things. And so it's the same thing as just integrating over b of the actual things. Okay, you can read it over b or b tilde. These things are defined to give you the same answer either place, by definition. And so there you go. I mean, by the way, I could just put a b tilde here and say it's in the coordinate chart. But the point is, this is the actual Gauss curvature on the surface. This is the area from the actual surface, right? So by definition, this equals this as well. And there you go. We have proved what I said we were going to prove, that the integral of this omega 2,1 is, in fact, the integral of the Gauss curvature, the integral over the one-dimensional boundary. In other words, it's because why? D of this omega form, you have a one form, omega 2,1, D of it is the Gauss curvature times the area form. And so what can we do with this? Well, the last step to really put things together is to use this identity we proved last time. Is to say, well, on the one hand, when you use Green's theorem, this integral equals this. But on the other hand, okay, I'm going to say from way over there, okay? In other words, this equals this equals this. We have this big train of thought, but now I'm coming back to here, okay? This is sort of the center of the computation, okay? When we integrate over the boundary of the curve of the geodesic curvature, well, I can just write that down, right? I can just say this is the integral over the boundary of B of the geodesic curvature, ds. Okay. So maybe it's easier to look at here. It's something ds, omega 2,1 of beta prime of s times ds. What is omega 2,1 of beta prime of s? It's this. So I get integral of geodesic curvature ds right? Minus d theta ds, and all this times ds, right? Okay, so, but wait a second, d theta ds, I can use the fundamental theorem of calculus here. This is just going to give me delta theta, right? What is delta theta when you go around once? Well, theta increases by 2 pi. And so what we get then is that that'll just be 2 pi. And let's take that minus 2 pi and put it to the other side. And so then what we're going to have then is 2 pi equals, and this has a minus sign, put it to the other side, the integral over b of the Gauss curvature dA plus the integral over the boundary of the ball of the geodesic curvature ds. And there you go. That's the Gauss-Bonnet theorem on a disk. So you have a disk, something that's topologically trivial like a disk. It's got a Gauss curvature on the inside. It's got a geodesic curvature along the boundary of the region. And the integral of the Gauss curvature from the two-dimensional region plus the integral of the geodesic curvature along the boundary, this always adds up to 2 pi. And we got the proof of the Gauss-Bonnet theorem on one board. You guys, just amuse me. I'm going to take a picture. I just I'm a little bit proud. I'm a little bit proud of this. A little bit proud. Okay. Oh shoot, Green's theorem's right there too. Oh, I gotta get your Green's theorem in there. Actually, I don't know if you guys agree with me, but sometimes mathematics takes on an artistic quality, a beautiful quality. And the ideas here are really beautiful. I mean, Gauss was impressed. If he's impressed, that should tell us we should be impressed. I'll make a random comment. You guys are not easily offended, right? The human condition. It's tough, isn't it? It's tough being human. And roughly speaking, the conclusion I've come to is that humans aren't, including myself, not an exception, right? We're not that smart, actually. We struggle to figure out how to just barely get by, right? And we should be modest, right? We should not be too impressed with ourselves, just because we're be able to get by a little bit better than these other idiots, okay? I mean, it's all relative, right? If we meet aliens from another civilization, I'm pretty sure they're going to find us mediocre at best. Or I hope they're kind. Let's put it that way. I hope they're kind. And the reason I mention this is that you take someone like Gauss. Yeah, he was smarter than most of the rest of us, all right? And the ability to judge awesomeness and what's genius and what's brilliant and what's incredible, that's something that is in some sense hard to do, and therefore only the most qualified among us, right, really get to say. And so when Gauss says something is awesome, then it's awesome, right? It's kind of almost by definition. We figure out who the people who have the most insight is. And then it's not a bad idea to say, okay, if they say something, then I'm going to think that the odds that it's true at least are higher, right? It doesn't make it true, okay? That makes it higher. And Gauss was very impressed by this. This is what what impressed Gauss? What made Gauss happy? This made Gauss happy, right? And so that's like, okay. Therefore, that's why it's like, go ahead and study a little extra hard for the final and learn this material for yourself, right? Because it'll be rewarding. Because this is, and I have to say, okay, then you come to your own opinion, of course, right? But this is a really cool theorem. It's super, super cool. And we're not even done, by the way. This is just the Gauss-Bonnet theorem for a disk. By the way, generalized Stokes theorem, also beautiful. And this is almost so beautiful. It's actually, it's almost so fundamental that it's trivial. Do you ever get the thing when you study something hard for a long time and then at some point you realize you don't get the sensation you've learned anything because it's all so fundamental and natural? So the generalized Stokes theorem is literally just d omega is defined to make this theorem true. And so at the end of the day, it's like, oh, tautology, right? It's like, did we prove anything? Or what, it's just the recognition that you can use the fundamental theorem of calculus to take integrals on boundaries of things and turn them into integrals on the interior. Okay, that's all it really is the recognition that you can do that. Oh, what do you get when you do that? Well, that's the definition of what that is. Okay. So now let's go ahead and flesh out the Gauss-Bonnet theorem. That's for a disk. Let's see here. I think I'm going to erase the middle board because we got the picture there.
Board over there.
There is, but then it won't be on the video.
Oh.
Yeah, you're being videotaped, by the way.
Really forgot that.
I tend to forget it myself. I hope the future people judge us kindly.
If it helps, this is probably also not on the video.
What's that?
This one is probably not on the video.
You can get a slight view of it, at least, you know.
Cool.
Yeah, but you're right, it's going to be hard for them to read. Okay. So we got this Gauss-Bonnet theorem on a disk. And here's, you guys all heard about Euler characteristic. We're about to get into that a bit. I'm limited on time, so let me, I'll tell you what Euler characteristic is at the end. It'll just sort of pop out. Because we can generalize this result. What if instead of a nice smooth disk, what if we had corners to our surface, right? And like it could be a triangle, right? So you're going around, you're integrating around the boundary here. So this is, I'm going to use D for disk, okay? And we use B over here, so it doesn't matter. And so we're going to integrate over the boundary, but as you go around, you have a turning angle here, right? And then you go around here, and then you're turning that much, and then you go here, and you're turning that much. So these things with corners, what you can do is you can round out the corners. Do you guys agree? And when you round out the corners, then this geodesic curvature, by the way, is just theta prime of s. Right? On small scales, it really is theta prime of s. And when you integrate theta prime of s ds, it's just delta theta. So what we can do is, let's have these interior angles. We'll call this theta 1, that theta 2, and that theta 3, okay? And so when you put in the Gauss-Bonnet theorem for a disk with corners, what you get then is that 2 pi is equal to the integral over the disk of kdA plus the integral over the boundary of the disk minus the corners, okay? So the corners we're going to treat separately, all right? Of the geodesic curvature, ds. And then plus, we need to put in a summation, and this is k over the number of however many corners there are. I'll just say a summation over k, of how much you turn in each corner, right? Because this integral of geodesic curvature, when you think of it as a really tight corner, right? That's going to give me this delta theta, and that delta theta right here, notice this is pi minus theta 2. Do you see that? So we're going to get a summation over k of pi minus theta k. You guys agree? If the interior angles are theta, then the exterior angles, how much you're actually turning at each point, right, when you round this out, is going to be pi minus theta k. Good. Now, by the way, you also get this formula. If you take the formula I had right here before I erased it, and remember there was an integral of theta prime of s ds, right, or d theta ds. Right? If you just break it up, define integrals, and then look at the discontinuities of theta at the boundaries, you get that formula as well. So this is the Gauss-Bonnet theorem for a disk with corners. And then what you do is you say, well, what if I have a surface with like a boundary? So this is now going to be a surface M, and this is the boundary of M, right? And what I'm going to do is I'm going to triangulate it. And triangulate means I can make it out of polygons, all right? But for example, a triangulation, I'm drawing you an example of a triangulation. dot, 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 okay? But maybe a simple example of a triangulation would be, a triangulation of a sphere would just be a cube, right? Because I'm using, but also I could use any of the Platonic solids, right? I could do a dodecahedron or an icosahedron or whatever, right? But what I'm doing is I want to understand it topologically as the union of a bunch of polygons, okay? Like this. Now here's the point. See this donut hole here? This thing can have topology. M can have topology. You can have any number of donut holes. It can have any boundary you want. Here I have a single S1 boundary, a single circle boundary, right? But I can have multiple circle boundaries, right? So there's a lot of different possibilities. But what I want to do with this, I want to take this identity here on each of these polygons, which are disks with corners. I want to write down this identity for each one, and then I want to add them all up. Okay, so plus sign, right? Add them all up. And what I want to do is, let's call this, this is like F1, this is F for faces, F2, F3, right? And so I want to integrate this over F I. I let I go from, and this is the boundary of Fi, right? And here we're summing over, this is theta, but it also depends on I, doesn't it? Okay? And so, well, what do you get? What you get is, well, I'm going to get, by the way, let's let F equal the number of faces, right? So how many of these polygons do you have? Well, I'm going to add them up for each face. Well, what I'm going to get then is 2 pi times the number of faces. Do you guys agree? That's what I'm going to get when I add this up on the left-hand side. And over here, I'm going to get the integral of, well, I'm integrating the Gauss curvature over each face, and the faces cover M, so really it's just the integral over M of the Gauss curvature times the area form, right? Fair enough? And then plus, then I take the integral. Well, here I'm integrating over the boundary of each of those triangles, so that's going to be a huge mess, right? Each of those polygons. But here's the thing. Geodesic curvature is, it's the rate at which you're curving in towards your surface, right? Because we have to say which way is positive and which way is negative. If you check our calculation, it's set up to where when you're curving in towards your surface, it's positive, but if you're curving away from your face, then it's negative. And so what you're going to see is, if I look at any particular, if I look at the boundary between two faces, like here's a triangle look like this, but then I have another one that goes like that. This thing is curving in. It doesn't really matter which way you go, by the way, this way or that way. This is curving in towards this face, but away from that face. So the geodesic curvature is positive on this one and negative on that one. They have the same length, so those integrals are all going to cancel. Okay? And so the only thing we doesn't cancel is when there's only a face on one side. So we get the integral over the boundary of M of the geodesic curvature times ds. All right? So it's like shaping up something interesting here. And then there's a couple of nice tricks to deal with this, okay? So this pi here, how many pi's do we have? Well, we get 1 pi for each angle for each polygon, right? But polygons have a special property. Triangles have 3 corners, but they also have 3 sides. Pentagons have 5 corners, but they also have 5 sides, right? So instead what I want to do is, let's associate this pi not with each corner, but with each side. Okay? And there's a reason to do this. So if you associate with each, so in other words, I get a pi here and a pi there. I get a pi for this side, both because it belongs to this triangle and that triangle. And so what I need to do is, when we're talking about these one-dimensional sides, they're called edges, okay? And we'll say E sub I equals the number of interior edges. And then we'll say E sub B equals the number of boundary edges. And so what I get for these pi's then is I get, well, each of these edges gets counted twice if you're on the interior, right? And so I get 2 pi times the number of interior edges, and then plus 1 pi for all the boundary edges. Did I do that right? Yeah. Okay. And then I have this minus theta thing, right? Now the thetas, remember, they're the interior angles, right? These thetas are the inside angles of each of these polygons, right? And it's basically saying add them all up, add up all the interior angles. Well, I don't want to do it one at a time. What I want to do is recognize, hey, you get 2 pi here. If you go all the way around a vertex, you get 2 pi, right? So each vertex is going to give me 2 pi. Except if I'm on the boundary, then I just get 1 pi. Right? Okay, so then what we have is minus 2 pi times the number of, well, now we got to talk about vertices, right? So the interior, we got number of interior vertices. And then we got VB, which is the number of boundary vertices. And so this is going to be minus 2 pi times the number of interior vertices, and then minus pi times the number of boundary vertices. Okay? And by the way, let's go ahead and let the sum of the number of edges, E, equal just EI plus EB, okay? The total, okay? And then the total number of vertices will just be VI plus VB. And so then what we have here is the integral over M of KdA plus the integral over the boundary of M of the geodesic curvature ds. And then what this equals is 2 pi times a bunch of stuff here, okay? Now what is a bunch of stuff? I'm going to use the eraser method just because it's a board thing and time is limited, okay? EB and VB, they're equal, right? The number of, if you think about how many vertices do I have on that circle, also equals the number of edges I have on that circle, right? Because why? The boundary of a two-dimensional surface is always a circle. Okay, we're supposing we have nothing but finite surfaces. Okay. So the point is that EB is equal to VB. Okay. And so you guys won't hold it against me then if I just go ahead and double both of these. Why? Because I increased it the same amount I decreased it, right? These two things are equal, so if I double both of them, I haven't changed anything. Fair enough? But now I just have 2 pi times the total number of edges, and I have minus 2 pi times the total number of vertices, right? And so, and then if we combine that, what we get is over here it's F, and then minus E plus V. And this right here is known as the Euler characteristic. Number of faces minus edges plus vertices. So what have we done? What have we done here? Let me just point this out. Let's take this cube here, right? This cube has number of faces is equal to 6. The number of edges is equal to 4 on the top, 4 on the bottom, 4 vertical, that's 12, right? And the number of vertices is equal to 8, right? 4 on the top, 4 on the bottom. I'm going to draw a line here, but remember it's F minus E plus V, so you get 14 minus 12, and what you get is the Euler characteristic is equal to 2. This is the Euler characteristic chi there. And so what this is telling us then is that the Euler characteristic of a sphere is 2. So we get 2 pi times 2 is equal to the integral over any sphere of the Gauss curvature times the area formed. Now there's something that should be bothering you right now. It's like, well, wait a second. What if I didn't triangulate the sphere as a cube? How do I know how? What if I triangulate it as a dodecahedron? Or what if I do a tetrahedron? Won't I get a different answer? Well, no. I mean, it can't be, right? Because it's amazing. Like, it's saying that this geometric quantity always equals 2 pi times an integer. And that integer, I mean, it can't change. I mean, this is true for any triangulation I do. It's always going to give me the right answer. So, for example, what if I triangulate the sphere with a tetrahedron, right? A tetrahedron has 4 faces. The number of edges is equal to 6, right? 3 vertical and 3 on the bottom. Number of vertices is equal to 4. 4 plus 4 is 8 minus 6 is 2. Still 2. Doesn't matter. So what we've proved using the Gauss-Bonnet formula is that when you triangulate a surface, even a surface with boundary, f minus e plus v is an invariant. It's a topological invariant. It can't change because it equals this geometric thing here, right? And so really why people love this and why this is one of my favorite theorems here. I mean, this is the Gauss-Bonnet theorem. This is like the full version of the Gauss-Bonnet theorem here. Is that you have geometry on the right-hand side and topology on the left-hand side. Now, by the way, is there an easier way to show that f minus e plus v is a topological invariant? Of course. It's actually not that hard to do. But this is the hardest way to show it's in a topological invariant. And furthermore, not only is it a topological invariant, it equals this. Right? It equals this geometry. Right? How do you show that the Euler characteristic is a topological invariant? Well, just take some triangulation you have of some surface, right? Okay, like a dodecahedron or something, right? And here's the observation, right? Is what if I add a vertex, okay? So you could add a vertex. Well, notice when you add a vertex, the number of vertices goes up by 1, right? But the number of edges, this one edge got split into 2 edges, so the number of edges goes up by 1 as well. And remember, the other characteristic is f minus e plus v. These have opposite signs, and so the Euler characteristic stays unchanged when you add a vertex. What if I split a face in 2 from an existing vertex to another existing vertex, right? Well then, so let's add an edge. Well then, the number of faces goes up by 1, right? And then I added an edge, so the number of edges goes up by 1. And again, it's f goes and e both go up by 1, but they have opposite signs, so again, the Euler characteristic doesn't change. So, and essentially, this is all you need to show. So you can show that given any triangulation of a surface, you can get to any other triangulation of the surface by doing these procedures and then the opposite of these procedures. And these procedures, and therefore their opposite, don't change the Euler characteristic. So it's also true, by the way, when you remove an edge or remove a vertex. Right? It doesn't change the Euler characteristic. And that's something I'll let you think about how you get from any triangulation to any other triangulation. But there's a purely topological proof that Euler characteristic, which is f minus e plus v, which for any triangulation of a surface is a topological invariant. And then this Euler characteristic. And so anyway, that's the Gauss-Bonnet theorem. Questions? By the way, this is usually the end of the course for most curves and surface courses in R3. It's sort of like the highlight of the course. For us, it's the end of the first 2/3. And so we've more or less covered what you have in your homework. And we'll be doing bonus topics starting with our next lecture. So you've got homework due. I think you don't really have homework due this week, but you have homework due the next week. No class next week. If I don't send out an email by Friday, please remind me to send out the email. But we're not going to have class next week. I'm out of town. But we will resume after that with pretty much, well, I'll take questions on this, obviously. And you may have questions with your homework and so forth. Start to prepare for the final exam and get all those homeworks done. And then we'll start on bonus material, which is, okay, now we understand curvature in 2 dimensions, right, for 2-dimensional surfaces, say in R3. Now let's go to higher dimensions and understand curvature more generally, which is it's all based on 2-dimensional curvature. All right, see you guys.